Chapter 4, Section 1. Chapter 4 is going to deal with aqueous solutions. We're going to review some items that we went over last year, and we're probably going to talk about some new things for the first time this year. So, aqueous solutions. We are talking about when things dissolve. So, when things dissolve, how does that work? Well, when things dissolve, we form solutions. Remember, in a solution, you have two things. You have the solvent and the solute. The solvent is present in the greatest abundance and usually what does the dissolving. So the solvent is in the greatest amount. Typically, in most of our labs, water is the solvent. It's possible to have other solvents, but remember the solvent is in the greatest presence. All other substances are solutes. So if I try and dissolve salt and sugar, those are my solutes. Water would be my solvent. And on the left here, you kind of see the molecular picture of how things dissolve. Methanol attaches itself to the water molecules and dissolves. Now, there's two types of things that can happen when something dissolves. We have two types of bonds. We have ionic and we have covalent. And we call the ionic molecule or the ionic bonds, they're called ionic compounds. When something bonds covalently, they're called molecular compounds. How they dissolve is different. So if we look here first, when an ionic compound dissolves, it forms ions. So an ionic compound dissolves, it forms ions. This process is called dissociation. So if I took salt is an ionic compound. When I dissolve that in water, that's going to break apart into Na plus and Cl minus. That breaking apart into ions is called dissociation. And then, as you can see on the molecular pic on the left-hand side, those ions attach to water molecules and dissolve. So the sodium is attaching naturally by itself right here to water molecules, and the chlorine is attaching by itself to water molecules. So when NaCl breaks apart, or any ionic compound breaks apart, it's called dissociation. Now, when they break apart, it's called an electrolyte. An electrolyte is any substances that turns into ions when dissolved in water. So mostly, anytime we have an ionic compound break apart in water, it's going to form an electrolyte. Now remember last year, when we talked about electrolytes, electrolyte was any substance in water that conducts electricity. So we were talking about simply in water, when it dissolves into ions or dissociates, we form an electrolyte. So an electrolyte is one that forms ions when it dissolves. A non-electrolyte does not do ions. So a non-electrolyte does not make ions. An electrolyte does form into ions. So what's an example of an electrolyte? Salt. NaCl is an ionic compound that breaks apart into Na plus and Cl minus. It's a great job in electrolyte. On the picture here on the left-hand side, we have an example of a non-electrolyte. Methanol, a type of alcohol, simply just bonds to the water molecules without breaking apart into any ions. Another good example of a non-electrolyte would be sugar. Sugar does not break apart into ions, it simply attaches itself to the water molecules. So an electrolyte is breaking apart into ions when it dissolves. A non-electrolyte does not break into ions when it dissolves. And if we take a look at all the compounds that we have across the spectrum, which ones are good electrolytes and which ones are not? Well, you can see here ionic compounds, all ionic compounds are strong electrolytes. That makes that simple. Where we muddy the waters a little bit is when it comes to molecular or covalent bonded materials, compounds. And when we talk about molecular compounds, strong acids are great electrolytes. Strong acids are strong electrolytes. Weak acids are weak electrolytes. And if any other compound, if it's not a weak acid or a weak base or a strong acid, it's not an electrolyte. Like sugar. Sugar's not a strong acid. It's not a weak acid or a weak base. Therefore, it's a non-electrolyte. So, this chart is going to be kind of extremely helpful when kind of figuring out the status of electrolytes and how things react when you put them in solutions in reactions. So what things classify strong acids? What are weak acids? What are weak bases? Well, we kind of already talked about this slide here. Molecular compounds tend to be non-electrolytes except for acids and bases. What are the acids and bases on that list? Well, a couple things here. On the top, you have three pictures and you have a light bulb. And we've talked about the presence of ions in solution. And if there are ions in solution and it's an electrolyte in water. Well, the left example is simply just water. There are no ions in pure water, so the light bulb doesn't light up. The second picture is sucrose. Sucrose is a covalent or molecular compound that is neither a strong acid or weak acid. Therefore, it's not going to light up the light bulb. And lastly, on the right-hand side, and I did this example last year, you have sodium chloride. Sodium chloride is an ionic compound. Therefore, it's going to dissociate or break into ions and form electricity. So only strong and weak electrolytes dissociate. Well, we talked about, we know ionic compounds did, but what about molecular? Well, kind of here's the list that will help you out. Here are strong electrolytes that are covalent molecules or molecular molecules. There are 7 strong acids: hydrochloric, hydrobromic, and hydroiodic. So the 3 halogens outside of fluorine. So the 3 halogens outside of fluorine are great. Then you have chloric, perchloric, nitric, and sulfuric. So you'll probably want to just come familiar with those strong acids. Strong bases is very simple. Group 1, anytime you have a base bonded with a group 1 metal, it's a strong base. And then anytime you have a group 2 metal under calcium and below is a strong base. So really, if you look at the first 2 groups on the periodic table, the only 2 elements that don't form strong bases are beryllium and magnesium. So a little piece of information there that's pretty helpful when you're talking about strong acids and strong bases. So everything on this list is a great electrolyte. Everything on this list dissociates greatly. So strong electrolytes we talked about, strong acids, strong bases, and soluble salts. Now when we talk about ions, we're going to talk about precipitation reactions. Precipitation reactions are simply just a double replacement reaction in which one of the compounds is insoluble and forms a precipitate, or that solid precipitates out of solution. Now we've talked about solubility rules last year. We will review them later in the year. We are really going to just focus on net ionic equations real quickly. So that's the last thing that we have in this slide. So we have a metathesis reaction, or just a double replacement reaction. What are our 2 products going to be in this double replacement reaction? You're going to have Ag bond with Cl, and you're going to have K bond with NO3. And their charges are balanced on both. Ag is +1, Cl is -1. K is +1, NO3 is -1, and this equation is balanced. Now, one thing that we're lacking is, are any of these a solid? Are any of these going to form a precipitate? Well, if we go ahead and jump ahead, remember it's important to label what each of these are. So AgNO3 and KCl in reactants are both aqueous solutions. Remember, aqueous means dissolved in water. Then if we look at the products, AgCl is a solid. All right, silver chloride precipitates out of that solution. Potassium nitrate is going to be the aqueous solution. What we are going to spend a little time at is looking at the net ionic equation. What ions are important in this reaction? Well, the only ions that truly are important are the ones that form the solid or the precipitate. The other ions, remember, are what we call spectator ions. They're just watching the rest of the reaction take place. So, what I talked about earlier comes back. We have to be careful about whether things are solids, liquids, or gases, or aqueous solutions. We need to make sure that we write those down when we do the reactivity. So we go back to the molecular equation of our example. Silver nitrate with potassium chloride, we get our two products. Let's focus on writing the net ionic equation. And all we did here from this step to the next slide is all we did in this first step is we broke apart everything into ions. So we just Ag and NO, Ag plus, NO3 minus, K plus Cl minus, Ag plus Cl minus, and K plus and NO3 minus. Then we broke it apart. Now what we're going to have to do is we're going to have to cross off things that are not important to the reaction. Well, what formed our solid? Our solid was AgCl. So we are going to cross off everything not important to AgCl. So you can see here, we crossed off NO3. We crossed off K. We kept Cl. We kept AgCl as our solid because it's no longer in ions. We cross off K. We cross off NO3. And what ends up being is we're going to write our net ionic equation is going to be Ag plus Cl minus. And AgCl is our solid. That is our net ionic equation because those are the only two ions that change in solution. They change into something different, they precipitate out, and they change into a solid. So if we take one last look at our reaction, we crossed off all ions that didn't matter. And remember, the ions that don't matter are called spectator ions. These are the ions that are simply just sitting in solution, watching everything else do the work. They just remain in solution and they stay there. So if we review doing a net ionic equation real quickly, you're going to have the equation. You're going to break the equation into its ions. Now, one thing I did not mention earlier is AgCl is a solid. Therefore, you can't break that into ions. It's attached together. It's no longer in solution, so you cannot break that into ions. So when we go to the second step, we have everything in solution except our solid. So we can break everything to ions except our solid. We cross off what's not important, or the spectator ions, and our net ionic equation is what helps form the solid. So here's just some couple steps if you really want to focus on writing down what a net ionic equation looks like. However, if you kind of get the gist of it, it's not too bad. And don't get caught up in doing solubility rules quite yet. We will talk about them tomorrow.